Hi guys, you're welcome to God Academy. In this lesson, I'll be taking you through Principle of Mathematical Induction. This is the second lesson in our algebra course. In our previous lesson, we looked at the introduction to algebra, number bases, as well as properties of numbers. We went through some examples. If this is the first time you are being on this channel, please subscribe so that we can move on supporting with content like this. So, principle of mathematical induction. What is the essence? In algebra, after learning number basics, you've got to know natural numbers, you've got to know whole numbers, you've got to know the rational numbers, integers. You also have learned irrational numbers which doesn't have representation, or under the broad raw number system. Now, the principle of mathematical induction is a nice principle for proving mathematical equation. So you say mathematical statement, or you can say equation. Now, assuming that you have derived the formula that whenever you add the square of even numbers, right? Sorry, let me make it square of even numbers. So assuming that you have derived an equation that is square of even numbers within the natural numbers space, okay? So if you have 2 squared, you have 4 squared, you have 6 squared, 8 squared, to the nth term, you realize that anytime you do the addition of consecutive um, even numbers within the natural number system space, you are always getting something like, so let me make it plus n squared, okay? You're always getting an expression, let's say n cubed over 4. Now, whenever you have an equation or you derived a mathematical relationship like this, you've got to prove to people that yes, this mathematical relation always holds for every particular number, right? Please, this is just an example I'm citing. Now, you can easily test for when you have the first case, that is 2 squared. You can test for when you have the two of them, that is when n is 2, considering 2 terms. You can easily test for when it's 3, 1, 2, and 3. But are you sure that you can test for every possible number of 10? That is a big no. Then, how do we prove that any mathematical statement I is true for all natural numbers, or depending on the number space you are considering? That is where the principle of mathematical induction. So the principle of mathematical induction uses 3 steps. First step, what we call the base step or the base case. Okay. Then we have the second step, which we call induction hypothesis. Induction hypothesis. Then we have the final step, which we call the inductive step. Inductive. So these 3 steps help us to find or to prove that every mathematical relation will be true or will hold for all possible natural numbers. So now let's look at the different scenarios and see how we can apply mathematical induction to solve problems. And a mathematical induction, we have different problems, and depending on the problem, it determines how you are going to prove. Okay, so the first type that you have is the linear case. Okay, when you have a linear sequence, which may be quadratic or cubic in itself. Okay, and the second one, you can have the um divisibility. Okay, divisibility. So the problem will ask you that you have a mathematical statement. Prove that that statement is divisible by a certain number. So you have to show that that statement will forever be divisible by that number they are talking about. The next one is factorial, the factorial problem. So we have problems that involve factorials, and we also have inequalities. Okay, equality. So these are some of the possible problems you encounter when you're doing algebra at these early steps. Now let's solve some couple of examples for you to understand this better. Let's check the first type. Okay, so the first type, I have a problem here. It says that 1 plus 2 plus 3 dots plus n is always equal to n multiplying n plus 1 all over 2. So this is a mathematical statement. The problem is that we are to prove that the statement holds for all values of n, which is a member of what? The natural numbers. Okay. So we have a mathematical problem here. We are to prove that this statement is true for every possible value of n. How do we do this? Now let's examine the mathematical system. Start working on any problem. You say that let p of n represent our mathematical statement 1 plus 2 plus 3 dots plus n equal to n multiplying plus 1 all over 2. This statement is trying to say that if you have the sum of a sequence of numbers, and these numbers represent natural numbers, okay, we have 1, 2, 3, 4, 5, 6 to the nth term. And what the formula is saying is when I add any number of terms within this sequence, it is always given by this formula. How true is this? Now, this is where we can apply mathematical induction. So let's start. So step one, we have the base case. Okay. The essence of the base case is to test for the lowest or the minimum possible value of n. If you claim that this statement is true for all values of n, then at least the least value of n should work. That is what the base case is to solve. So how do we test for base case? In our scenario, we can test for base cases for n is equal to 1, for n equals 2, 3, or any, okay? So you only have to confirm the base case for 1. So if you want to validate by finding for 2, for 3, fine, it's also allowed. But please, for the exam purposes, you make sure that you stick to the number 1 or you stick to the least single possible value of n, which is the lowest to test, okay? So now let's see. So testing our base case, we will come to our mathematical statement. For n is equal to 1, what happens? On the left side of the equation, we can only find the first term. Please, there is this popular error or common error that students, whenever you see the n here, okay, we are trying to sum a sequence, okay? So we have the first term, the second term, the third term, so the nth term. For n is equal to 1, we are looking for the first term. So on our left hand side, you can see that the first term is equal to what? 1. On our right hand side, what do you see? We have a placeholder which is n multiplying n all over 2. This means that for us to find the value of our statement at a particular n, you will simply replace the value of n here. That is all. So at n equals 1, which is the first term, the formula will give us 1 multiplying 1 plus all over 2. This maps 1 times 1 plus 1, 2 over 2. That gives us what? 1. Therefore, LHS is equal to RH. Therefore, our base case is true. As simple as that. So you say that we simply conclude that therefore base case is true and you are done proving. So you can go forward to test for other base cases. Now let's try testing for when n is equal to 2. So you say that for n is equal to 2, what do you see? On the left hand side, we have the first two terms being qualified. What are the first two terms? We have on my LHS, I'm going to have 1 plus 2. And that gives me, because I'm summing the first two. As I said, for n is equal to 2, the first two, okay, that is giving me 3, right? Now, my right hand side, what is happening at my right hand side? I simply put the value of n inside the equation, and I'm going to have 2 multiplying 2 all over. This gives me 2 multiplying all over 2. This cancels this, and so 3 and 3 are the same. Therefore, our base case is true. Let's move to the second step. The second step is what we call the induction hypothesis. For induction hypothesis, at this step, we don't solve, but we assume. That is the word hypothesis. We assume that our statement is true for a particular unknown. This is a very important step in mathematical induction. Now, our statement P of n, we are going to assume. So, assuming that the statement is true for n, so for n is equal to k. So therefore, we are assuming that our statement is true. Without assumption, we cannot actually prove. So if you are saying that you want to prove that this statement is true for every natural number, then we can assume that the statement is true for a particular unknown, right? So this is what you are doing this step. Therefore, our statement simply becomes P of k is equal to 1 plus 2 plus 3 dots plus k is equal to k multiplying k plus 1 all over 2, right? Now we are saying that this statement that you see here is perfectly okay. So this is, and that ends the induction, as simple as that. You can clearly see we tested for the base case, then we came to induction hypothesis. Everything works in. Now let's move to the main step, which we call the inductive step. Inductive. At the inductive step, this is where the major calculation or manipulation. We have already tested that our statement is true for the worst case or for the least case. We have assumed. Then now, at the inductive step, what we are trying to do is we want to test that if our equation or our statement is true for the unknown k, then it should be true for k plus 1. That is the next step. That will tell us that for every value of k is true, then k plus 1 is true. Then it means that our statement will be true for every possible natural number. So let's see. So here what we say is proving for n is equal to k plus 1. That's it. So we have to prove that our statement will be true for n is equal to k. Therefore, this is what we are looking for, p of k plus 1. Okay, that's what you are looking for. Now, what is p of k plus 1? P of k plus 1, you can say that you get 1 plus 2 plus, please, k plus 1 is the next term after k. So at this point, there will be changes. Take note of that change. I'll have plus k, then plus k plus 1. Because when I have 1, I move to 2. I just added 1, right? I'll add 1, I'll move to 2. If I want to find for k plus 1, it means that I've got to add 1 to k, then add it as part of the sequence. This should give me the expression on my right, wherever I see k, I'll put k plus 1. Okay, I'm going to have k plus 1 outside for this particular k. Multiplying the k inside also becomes k plus 1 all over 2. So now this gives 1 plus 2 plus 3 dots plus k plus 1. Okay, and this should give us k plus 1 multiplying k plus 2 all over 2. At this point, there is something interesting here. We realize that from this side of our inductive hypothesis, where we have 1 plus all plus k is given as this. We have already confirmed that this is true. Because of that, when I come here, I can replace all this side with the value I got here. Because I'm saying that 1 plus 2 plus up to k is always equal to this. That is true. So that is the most important part of induction hypothesis. So here, I'll simply replace this with k multiplying k plus 1 all over 2 plus k plus 1 would give me k plus 1 multiplying k plus 2 all over 2. Our whole task is to make sure that the left hand side is equal to the right hand side. Then we can say that the statement p of n is true for every possible value of n. Okay. So here, let's simplify. I have k plus, sorry, so here I'll get k squared plus k, okay? When I expand this bracket, this over 2 plus k plus 1 equal to, now this expression you simplify. K multiply k, we get k squared. K multiply 2, we get 2k. 1 multiplying k, we get k. Then 1 multiply 2, we get 2. Everything over 2, okay? Now, at this point, what do? We simplify algebraic expression. This is number 1. We cross multiply. I'm going to have k squared plus k, right? Then I'll have plus 2 multiplying k plus 1, because this is cross multiply, okay? All over. It gives us k squared plus 3k plus 2 over 2. That is this. Let's further simplify here. That side, we can get k squared plus k plus 2k plus 2. I only expanded this here, okay? All over 2. And this is equal to k squared plus 3k plus 2 all over 2. So I'll simply get k squared here plus 3k plus 2 all over 2 equal to k squared plus 3k plus 2 all over 2. Since my left hand side is equal to my right hand side, we conclude that the statement p of n true for all values of what? N. Thank you. So this is how we solve mathematical induction. That is just one simple example I've taken. Let's look at another example. Equations always don't come as easy as you saw. Now let's see the second example. I have an interesting problem here. It says that prove that the statement or the expression n cubed plus 2n is divisible by 3. Simple as that. Can you imagine? Sorry. So the statement n cubed plus 2, right, divisible by 3. Solution. How do you solve this? This is a perfect mathematical induction problem. You want to prove that the statement n cubed plus 2 is divisible by 3. Therefore, we go through the same process. Base case or base step. Here, we have to prove for what? N equals 1, okay? So in our base case, for n equals 1, what are you getting? Get 1 multiplied to the power 3. Wherever you see n, you put 1, okay? Have you realized this is different from the problem you solved by the same concept? 2 multiplying 1. This gives me 1 cube is 1, 2 times 1 is what? That is equal to 3. Is 3 divisible by 3? That is true. So our base case, simply write base case. Once we've got to know our base case, we move to induction hypothesis. Induction hypothesis. For our induction hypothesis, as I said, we are simply assuming that our statement is true. Okay, so assuming that the statement is true for n is equal to k. Therefore, our statement becomes k cube. Okay, take note. This is our statement n cube plus 2n. Okay, so you can represent it with symbol as p of n or anything that you prefer. So I'm going to have at n equals k, I'm going to have k cube plus 2. And you are saying that this, it being true, means that it is divisible by 3. You have accepted that anywhere we see expression divisible by 3. Take note of that. Let's quickly go through our induction step or inductive step. At our inductive step, you have to prove that the statement is true. Okay, statement true for n equal to k plus. So at this point, wherever I see, you go back to it. Wherever I see n, you put k plus 1. So k plus 1 all cube plus 2 multiplying k. You have to prove that this is divisible by 3. So as simple as that, we expand it. Expanding, I'm going to have k cube using binomial expansion plus 3k squared plus 3k plus 1, right? Then plus 2k that we have here. Sorry, here is 2n, so we are looking for k plus 1, so k plus 1. Okay, I'm going to have 2k plus 2. Take note of that. Simply simplify this expression. You get k cubed plus 3k squared plus 3k. 1 plus 2 will give me what? Give me 3, right? Then I have plus 2k, right? Then with plus 2k, we are just to make sure that we can conclude this expression here is divisible by 3. From our induction hypothesis, we said k cubed plus 2k, that is always divisible. So here, let's see, let's group k cubed plus the 2k that we have here at one side, which we know that this is divisible by 3 according to our induction hypothesis. Here we can have 3k squared, then we have what? 3k plus 3, right? So these are the leftovers. How do we determine that the rest of the, so I can come down k cubed plus 2k, right, in one bracket. Then I'll factorize 3 out because you can see 3 is common for. I'll have k squared plus k plus 1. I can clearly see that this expression here is by 3. Is that not it? Because my hypothesis says that it's true. Now, there's one thing that we could have done. If the hypothesis is true, we can equate the hypothesis to an unknown, say 3m. Okay, we just represent this with an expression that will show that our expression here is equal to a number that is divisible by 3. So let's assume it's, when I come here, I'm simply going to write 3m plus 3. You get the expression, right? K squared plus k plus 1. You can clearly see that here I can factorize 3 out. So this whole expression here is divisible by 3. And therefore we see that our statement is true and is divisible by what? Now, let's solve for our last problem, which here we are going to observe how we can solve problems involving factorial and also inequality. Okay, it's very important. That. Okay, so my equation 3 or my problem 3, I have that prove that 2 to the power n is less than n factorial for n is greater than or equal to 4. So this is another problem, but here you can see it's a combination of inequality and a factorial. How do we use the mathematical induction system? Usually we test for our base, but take note of the change. The base case now we can't use n equals 1 because our statement brought its own condition that n is greater than or equal to 4, right? So here our base case is when n is equal to 4. As I'm going to have when n is equal to 4, my left side I'll have 2 to the power 4 is less than 4 factorial. 2 to the power 4 is simply 6. It's 4 factorial is 24, right? Therefore, this is true. Our base case. Therefore, our base case is true. Base case. If our base case is true, then what do we do next? We go to our hypothesis. So our hypothesis here will simply assume that for n is equal to k is true. So assuming the statement true for n is equal to k. Okay. Therefore, my statement becomes 2 to the power k less than k factorial for k is greater than or equal to this statement. Now let's quickly do our inductive step. At our inductive step, what is happening? We realize that here we have to prove for n is equal to k plus 1. Prove for n equals k plus 1. I go back wherever I see n, I put k plus 1. I'm going to have 2 to the power k plus 1 less than k plus 1, right? As simple as that. We can break this expression down to 2 multiplying 2 to the power k. That's indices decompose. Okay, this is less than. If you have an expression in a factorial, it means that, so let's say 2 factorial is the same as 2 times 1 times what? You end at 1, okay? So whenever you have something like 8 factorial, it's the same as 8 times 7 times 6 times 5 up towards 1, okay? So you're always going to deduct 1 from the number. So the number reaches 1. We don't add 0. Otherwise, everything. Therefore, having talked about that, we can expand our factorial side. And simply, we're going to have this. So my 2 multiplying 2 to the power k is less than the expression. This expression will always start whenever you are doing factorial. The number itself starts. So I have k plus 1 multiplying k plus 1 minus 1. That will give me, and it will give me k minus 1. But let's end here. Don't remove the factorial because you are not done. Whenever you are dealing with unknowns, because the unknown doesn't have a fixed value, you cannot remove the factorial. Factorial is removed when we reach only 1. Okay, take note. Now, our statement is saying that 2 multiplying 2 to the power k is less than this. How true is this? Let's see how we use factorial and inequality to solve this problem. You realize that 2 times 2 to the power k, in my hypothesis, I've assumed that 2 to the power k is always less than 2 multiplying, it's always less than k factorial. Therefore, this is true. I can use that to compare what I have here. We cannot tell a class 6 student or a grade 6 student that this expression here is bigger than this. You can't say that. You have case. Let's prove that indeed this. I have this statement which we all have agreed that is true. That whenever I see to the power k less than k factorial, multiplying through by 2, I'll get an expression 2 multiplying 2 to the power k. I'm multiplying through my assumption by 2. It's less than 2 times k factorial. Okay. Once I've done this, I can see that 2 times 2 to the power k is the same thing here. And we are saying that this expression is less than 2 times 2 is less than 2k factorial, right? That means that this expression is true because anything you do to your hypothesis is true. Okay. So yeah, I'm going to have 2 multiplying 2 to the power k is less than 2k, right? Open bracket k times k minus 1. Take note, factorial, because we have expanded the factorial sign. Now let's see. You can clearly see that on my right side here, I have k minus 1, I have k minus 1, I have k, I have k. I have what 2, but here I have k plus 1. And we are saying that 2 multiplying 2 to the power k is less than this. If 2 to the power k is less than this expression, then it means that we can compare this expression and this expression. The one which is big, then we can confirm. This expression and this expression, which one is bigger? As I said, we have k minus 1 here, we have k minus 1 here, factorial. They will all cancel. It's the same thing. We have k, we have k. The only difference that can help us distinguish which one is bigger is 2 and k plus 1. Let's analyze 2 and have k plus 1. Remember that our condition only works when k is greater than or equal to 4, meaning that the k value here can never be 3, can never be 2, can never be 1, but can be 4. Using the least case of k is 4 plus 1, that is 5. Therefore, this here is bigger than 2. Because of that, this whole expression here is bigger than this. But from our inductive hypothesis, we realize that 2 multiplying 2 to the power k is always less than this, right? Meaning this one is bigger than this. If this small number here, which when you compare to this one is bigger than this, it's even bigger than 2 to the power, 2 times 2 to the power k. It means that this expression here too will be bigger than this. And that is how we prove our we prove our mathematical induction, as simple as that. Therefore, our statement is true. I mean, this is very logical. That's how we use it. Okay? Whenever you're doing factorial, it's logical. We compare. We realize that it was only k plus 1 and 2 that was making the difference. We analyze and we realize that from the coefficient, k plus 1 is bigger than 2. Therefore, this expression is bigger than this. And if this is bigger than 2 multiplying 2 to the power k, then this will be bigger than 2. Thank you for being with me in this video. Please don't forget to subscribe to this channel to promote us. This channel has been over a year and has served a lot of students, but we still not hit that 1k. Please subscribe and make it work.